Hello there and welcome to section 10.1 on Taylor polynomials. We're going to kick things off here with somewhat of a throwback to Calc 1 and discuss linear approximation, which is also known as linearization. And so let's say we're looking at the graph of a function f near the point where x equals a. And let's say we want to approximate this function near x equals a with a linear function that in some sense best approximates this curve near the point a comma f of a. Okay, so graphically we're looking to draw a line that passes through this point in red, and if this line is going to do a good job in approximating the curve, we'd like the slope of the line to equal the slope of the curve at x equals a, right? So from Calc 1 you recognize that as the tangent line to the curve at this point in red, and so I'll go ahead and put in that tangent line, and we're going to call this tangent line P1 of x. Okay, this is known as the first Taylor polynomial of the function f based at a. And how do you write down the equation of the tangent line at a point? Well, first off, note that the slope of this line, as we said, is equal to the slope of this curve. And the slope of the blue curve is just f prime evaluated at a, and that's what you see right here, right? This is the m part of this linear equation. And now just go back to point slope form of a line, right? This is x minus x1. Here x1 is just the x coordinate of the point our line is passing through, which is a. And then this is your y1, which is the y coordinate of the point that we're passing through, and that's just f of a. Okay, so this is the equation of this green tangent. Okay, so just make a note here, right? Again, this is just the tangent line to the curve at x equals a. And then two notes here. Note that if I plug a in for x, I'm going to get an a minus a, which is 0. So this whole term right here will drop out, and I'm just going to be left with f of a. And that's simply an expression of the fact that this line in green passes through the point a comma f of a. Note also that if you take the derivative of p1, well, f of a is constant, so its derivative is 0, and f prime of a is also constant, so we're really just differentiating x minus a, and that has a derivative of 1, so 1 times f prime of a will give us that p1 prime of a is equal to f prime of a, and this is just an expression of the fact that the slope of this green line is equal to the slope of the blue curve at x equals a, as we've already noted. All right, cool. Last thing I want to say here is that we're going to refer to this function p1 of x as the linear approximation to the function f for x close to a. Okay, so as you can see here, or as long as we're reasonably close to a, the values on the green tangent line and the values on the blue curve will be reasonably close. And we'll say a little bit more about, bounds on the error in this approximation a little bit later. But for now, I'd like to go ahead and look at two examples. So on the worksheet up here above, this is really just a summary of what we just discussed. And then it goes on to say, compute the first Taylor polynomial for each function at the specified point. Then use this polynomial to approximate the function at certain values and compute the absolute error in each approximation. Okay, so for part A, we're looking at f of x is equal to e to the x, and a here is equal to 0. All right, so to compute p1 based at a equals 0, well, I want f of 0, and that's just e to the 0, which is 1. And then I need f prime of 0, and f prime of x is just e to the x, and so f prime of 0 is e to the 0, which is also 1. So you go ahead and put that all together, and we find that p1 of x is equal to 1 plus x. Okay, so here is a picture. There is our exponential curve in red. And then our function p1 of x, well, that's 1 plus x. So I put that in, I can see, yeah, right? There is our linear approximation. If I zoom in a little bit, the values on this blue tangent line, right, look very, very close to the values on the red curve. All right, so now let's go back. We're now asked to approximate the value e to the 0.05. Okay, well here note that e to the 0.05 is just f of 0.05. And from what we just discussed, right, f of x will be approximately equal to p1 of x as long as x is reasonably close to our a value. So in other words, as long as x is close to 0 here, and 0.05 is reasonably close to 0, okay, the function value f of 0.05 will be reasonably close to p1 evaluated at 0.05. Okay, so if I go ahead and plug in 0.05 into what we just found for p1 of x, we get an approximation of 1.05 for this value e to the 0.05. All right, cool. So let's go back to that picture real quick. If I go ahead and put this point here in red, which is just 0.05 comma f of 0.05, in other words, just the point on the red curve when x is 0.05, so the height here is e to the 0.05, right, the value we're approximating. Now if I put the corresponding point on the blue line, right, from this view, they look almost basically indecipherable, right? Now if I do zoom in more, I can see, oh, there is of course a gap, right? But if you look at the scale over here, I can see while there is a gap, it does seem reasonably small. Okay, so now for the last part here, it says compute the absolute error in each approximation. That's where we're just going to use our calculator and find the difference between e to the 0.05 and 1.05 in absolute value, and this comes out to be about 0.00127. Okay, so reasonably good there in terms of our approximation. Now, of course, with any approximation, the question is always, how good do you need it to be? So if you need it to be within, say, a tenth, hey, we're doing really, really good here. But if you need it to be within, say, 10 to the negative sixth, yeah, maybe you need to do a little more work, okay? But in any event, let's check out part B. Same idea here. So we're looking at f of x, which is the square root of x. And now a is equal to 4. And then we're going to approximate the square root of 3.98. All right, so just as we saw in part A, I'm going to first look at f of 4, which is right here. And that's just the root of 4, which is 2. And then we want f prime of 4. So f prime of x, that's 1 over 2 root x. So if I plug in 4, I'm going to get 1 over 2 times the root of 4. Well, that's 1 over 2 times 2. That's a quarter. So I put all of that together, and I get that p1 of x is 2 plus a quarter times the quantity x minus 4. Okay, now you could multiply that all out and simplify a little bit, but actually I recommend just leaving it in this form for reasons that will become apparent a little bit later on. There's a lot of advantages just to leaving things in this form, in part because all the action is happening at our value a and close to a. So in this case, a is 4. You can see this thing is based, or in other words, centered at 4. And again, there's some nice things that come about from that. But in any event, let's go ahead and use p1 of x to approximate the root of 3.98, which is just simply f of 3.98. And just like in part A, that's going to be approximately equal to p1 of 3.98, right? So if I plug in 3.98 into p1, I get 1.995. Okay, so absolute error. If I look at the difference between the square root of 3.98 and our approximation, which is 1.995, okay, in absolute value, wow, this is a really, really small difference, right? We got 1, 2, 3, 4, 5 zeros and then 6266. So we don't have to really work very hard to get a rather accurate approximation there to this square root value. All right, well, that's going to do it. In the next video, we're going to just step things up a degree and look at quadratic approximation. All right, and that's going to be known as the second Taylor polynomial. All right, I'll see you there. Thanks.